This is the second of 2 videos on limiting reagents. In this video, we're going to work through some problems involving limiting reagents. In this first problem, we're going to look at the reaction of dihydrogen sulfide plus 2 methyl iodides forming dimethyl sulfide plus 2 hydroiodic acids. If we have 15.40 grams of methyl iodide and we add that to 1.97 grams of dihydrogen sulfide, how many grams of dimethyl sulfide will we produce? So what the problem is asking is how many grams of dimethyl sulfide are going to be produced. Items that we know or that we can calculate easily are, first, we can see that the equation is balanced. The second thing is that our stoichiometric ratio is 1 mole of dihydrogen sulfide to 2 moles of methyl iodide to 1 mole of dimethyl sulfide. We're starting with 15.40 grams of methyl iodide. We're starting with 1.97 grams of dihydrogen sulfide. And we can calculate the formula weights of dihydrogen sulfide, methyl iodide, and dimethyl sulfide. I'm now going to work out steps 3, developing a strategy, and 4, implementing that strategy by hand. We're now going to go through and we're going to develop our strategy. We're going to start with the answer and work to the beginning of the problem. The mass of dimethyl sulfide is simply equal to the number of moles of dimethyl sulfide we have times its formula weight. The number of moles is going to equal its stoichiometric coefficient times the reduced molar amount of the limiting reagent. And that's going to equal 1 times the reduced molar amount of the limiting reagent. The reduced molar amount we can calculate from the number of moles divided by the stoichiometric coefficients of our reactants. For dihydrogen sulfide, that's the number of moles divided by 1. For methyl iodide, that's the number of moles of methyl iodide divided by 2. We need to figure out which is the smallest, and that will be our limiting reagent. The number of moles is simply equal to the mass of the substance times the inverse of its formula weight. Going through and implementing this strategy now, number of moles of dihydrogen sulfide is equal to its mass times the inverse of its formula weight, which equals 0.0578 moles. Number of moles of methyl iodide is equal to its mass, 15.40 grams, times the inverse of its formula weight, 141.54 grams, equals 0.108 moles. H2S, determining its reduced molar amount, number of moles we have divided by 1, which is just 0.0578 moles. Methyl iodide, number of moles we have divided by 2, that equals 0.0542 moles. H2S is more, which means that methyl iodide is our limiting reagent. Number of moles of dimethyl sulfide we're going to produce is 1 times the reduced molar amount of our limiting reagent, which is 0.0542 moles. Taking that and multiplying it through by its formula weight gives us the mass that we'll produce. Which equals 3.37 grams. The answer that we obtained was 3.37 grams. We're now going to go through and use estimates to determine if that's a reasonable value. We're going to estimate the formula weight of methyl iodide as 150 AMUs and its mass as 15 grams. Going through, we can use those values and approximate the mass. Going through, we can use those values and approximate the number of moles of methyl iodide available to us of 0.1. If we divide through by its stoichiometric coefficient, we get 0.05 moles. We're going to approximate the formula weight of dihydrogen sulfide as 30 AMU, and its mass is 2 grams. The number of moles of dihydrogen sulfide we can therefore estimate as 0.06. Based on our reduced molar amounts, we say that methyl iodide is our limiting reagent. We're going to approximate the formula weight of dimethyl sulfide as 60 AMUs. The mass of dimethyl sulfide that we should be able to produce should equal its formula weight, 60 AMU, times the reduced molar amount of the limiting reagent, 0.05 moles, times its stoichiometric coefficient, 1, which is approximately 3 grams. 3 grams is close to the 3.37 grams that we calculated. In our second problem, we're looking at this combustion reaction. We have 4 C7H9NO molecules plus 39 O2 molecules, yielding 28 carbon dioxides, 18 waters, and 4 NO2s. If we react 87.6 grams of that carbon-containing compound and 119 grams of dioxygen, we're going to form 118 grams of CO2. What the question is asking, how many more grams of the limiting reagent would we need to add into the reaction in order to obtain a quantitative yield of the CO2? Based on the reaction stoichiometry, this looks like it might be a daunting problem. However, we can treat these exactly like we've treated all previous reactions. We just have larger stoichiometric coefficients and more of them in front of the various molecules. Going through our problem-solving strategies, what are we being asked? What we're being asked is how many additional grams of the non-limiting reagent need to be added to the reaction to obtain a quantitative yield of products. What we know is that 1, the equation is balanced. 2, we have a molar ratio of 4 moles of the carbon-containing compound to 39 moles of dioxygen. We start with 87.6 grams of C7H9NO. We start with 119 grams of dioxygen. The formula weight of dioxygen is 32 AMU, while the formula weight of C7H9NO is 123.15 AMU. I'm now going to work out steps 3 and steps 4 by hand. We're now going to go through and develop our strategy in much the same way we've done before. What we want is the mass, and that's just going to equal the number of moles times the formula weight. The number of moles is going to equal the number of moles of our non-limiting reagent, just the amount that's left over, divided by the stoichiometric coefficient of the non-limiting reagent, times the stoichiometric coefficient of the limiting reagent. The number of moles that we have left over of our non-limiting reagent is the number of moles we initially had minus the stoichiometric coefficient of the reduced molar amount of the limiting reagent. The number of moles that we have of C7H9NO is equal to its mass times the inverse of its formula weight. Number of moles of O2 that we have is equal to its mass times the inverse of its formula weight. The reduced molar amount is simply going to be the number of moles that we have of the two substances divided by their stoichiometric coefficient, 4 for C7H9NO and 32, no, that's its formula weight, 39, and we just want to know which is the smallest. Going through and implementing this strategy. The number of moles of C7H9NO that we have is equal to its mass, 87.6 grams, times 1 over its formula weight, 1 mole per 123.15 grams. That equals 0.711 moles. Number of moles of O2 is going to equal 119 grams times 1 mole per 32 grams, which equals 3.73 moles. Looking to see if O2 is our limiting reagent, we take 3.73 moles divided by 39. That equals 0.90954 moles. For the carbon-containing compound, 0.711 moles divided by 4 equals 0.178 moles. The O2 is less, so therefore it's our limiting reagent. The number of moles of C7H9NO we have left over equals 0.711 moles minus 4 times 0.0954 moles, and that equals 0.3294 moles. Now going to continue this on a new sheet of paper. The number of moles that we have of C7H9NO that we have to react with O2 with, that's the amount that's left over, is 0.3294 moles. The number of moles of O2 that we need to react with that is that amount divided by the stoichiometric coefficient of the carbon compound times the stoichiometric coefficient of O2, which is 3.211 moles. The mass of O2 that we need is just those number of moles times its formula weight, 32.00 grams per mole, which equals 102 grams. We obtained a value of O2 that we need of 102 grams. We're now going to use estimates to determine if this is a reasonable amount. We're going to round the amount of O2 that we have to 120 grams and its formula weight to 30 AMU. 120 divided by 30 equals 4 moles. Divided by 40, its approximate stoichiometric coefficient. We obtain 0.10 moles as its reduced molar amount. We're going to round the amount of C7H9NO we have to 80 grams and its formula weight to 120 AMU. If we take 0.75 moles divided by its stoichiometric amount, 4, we get 0.20. This is double the amount of O2. O2 is our limiting reagent. If we multiply that through by 40, its stoichiometric coefficient, and 30, its approximate molar mass, we get 120 grams. This 120 grams is close to our 102 grams that we obtained from working out the reaction. That brings us to the end of this video. In our next video, we'll be talking about water as a solvent.